New pictures captured by the James Webb Space Telescope have stunned researchers. Instead of expanding our perception of the universe, these pictures revealed a disturbing reality. Our ongoing comprehension is lacking in grasping the possibilities of the universe in its early stages. Where the hypothesis of the Big Bang appears to reach its limits, this drives us to contemplate new theories about its beginnings. The question arises regarding how the universe was shaped comprehensively, and why this new discovery challenges even the most experienced researchers to learn more about the Big Bang and the complex details of the revelation. Let's examine the concept of the Big Bang itself. In spite of mainstream thinking, the Big Bang was not an explosion in pre-existing space. Rather, it was space itself that began approximately 13.8 billion years ago, along with matter and time. From a singularity in physics and cosmology, a singularity describes points where gravity is so intense that the curvature of spacetime becomes infinite. Today, after billions of years since the beginning of the universe, we see that our vast home is part of a grand cycle. For experts, this represents a fundamental aspect of the universe since its very existence. It's clearly a continuous expansion. However, it's crucial to understand that the universe isn't drifting into pre-existing space. Rather, space itself is continuously expanding in size. According to current theories, the first stars began to shine somewhere in the range of 200 to 300 million years after the Big Bang, marking the end of the so-called Dark Ages. This was when the first luminous celestial objects coalesced to form mature galaxies. However, how quickly these galaxies formed remains a puzzling mystery. A wealth of data emerged through the first pictures obtained by the James Webb Space Telescope in July 2022. Experts reported that the telescope had detected various galaxies, some of which had already existed around 300 million years after the formation of the universe. However, in contrast to the infinite structures formed much later, these early galaxies were significantly smaller and less massive. This aligns perfectly with the scientific model accepted by researchers. The density of matter in the early universe was simply not sufficient to give rise to galaxies the size of those observed today. What began as the detection of 6 glowing red-shifted spots from the James Webb Telescope ended up triggering one of the most significant astronomical emergencies in recent times. Although these newly discovered galaxies are comparable in age to previously recorded galaxies, they are as massive as our own Milky Way. This has created an intriguing mystery in cosmic investigation. After examining a series of images captured by the near-infrared camera, experts identified the aforementioned light sources, using redshift to determine that the light from these objects took more than 1 billion years to reach our eyes on Earth. Consequently, we are dealing with structures that had already existed around 570 million years after the supposed Big Bang. By analyzing the characteristics of these structures, it was concluded that the Webb telescope had captured 6 early galaxies in the images. Remarkably, these galaxies were so massive that they challenged standard assumptions in cosmology. Instead of finding the typical smaller galaxies, structures were identified that were nearly as large as our own Milky Way. Despite having formed early in the universe's history, if we continue to analyze the data gathered by the James Webb Telescope, this gravitationally bound cluster of stars was already more than 10 billion times the mass of the Sun at that time, with one potentially surpassing the 10 billion solar mass mark. However, whether this scenario is accepted, the mystery remains unresolved. Even in this case, there would be significantly more luminous mass in the early universe than previously expected, presenting a conundrum. The identified objects contradict almost all traditional cosmological theories. Regardless of whether just one of these galaxies turns out to be real, it would challenge our prior assumptions. Furthermore, the density of matter in the early universe would have had to be several times greater than previously expected to account for this phenomenon. Another similarly strange explanation hinges on how these galaxies formed in a manner that remains entirely obscure to us. These discoveries and the discussions surrounding the Big Bang have prompted many researchers to drift away from this theory. Numerous astrophysicists with alternative viewpoints feel their perspectives are not being heard in scientific journals. Even those who express doubts about existing theories are often labeled as unjustifiable impulses. Yet, it is clear that even researchers who still advocate for the Big Bang theory are continually confronted with questions without definitive answers. These inquiries include specific issues like why and how, 13.8 billion years ago, something literally emerged from nothing? Could something genuinely start from nothing? Or was there some triggering event? Or was it all merely a coincidence? Steven Weinberg pointed out that the concept of time as we know it began solely with the Big Bang. Consequently, this process could not have been triggered by something outside it. A similar contentious question relates to the uniformity of radiation and density throughout the universe. Regardless of which direction or at what distance we look on a larger cosmic scale, we find similar densities and distributions of galaxies, nebulae, and radiation everywhere. Conventional analysts explain this phenomenon through the theory of cosmic expansion. However, various experts take this assumption further with a theory of turbulent expansion. According to this idea, expansion has only ceased in specific regions, like bubbles, and continues indefinitely elsewhere. This suggests that different universes could be forming in these bubbles, each with its own unique physical laws. Within this model, a significant question arises: what if the universe does not represent the entirety? More intriguingly, what if another universe existed before our own? In this case, the Big Bang would become part of a larger cycle. According to this perspective, our universe is part of a greater diverse structure. Within this framework, the possibility of a timeless cycle of breakdown and revival of the universe is advanced. However, this isn't the only viewpoint presented in the realm of cosmology. Aside from the theory of the universe's beginning in 1955, for instance, an article appeared in NASA Spacetimes arguing that there might have never been a Big Bang, since the universe has existed for an infinite time. In this view, the expansion of the universe would be non-existent, and the steady arrangement of matter could give the impression of a constant expansion. Moreover, another intriguing hypothesis emerges from the realm of quantum physics and string theory. Some tests have suggested that our universe and everything in it may essentially be a flat 3D image projected onto a surface. Thus, there is a possibility that our reality is a product of a higher simulation. While this might sound like the plot of an eccentric science fiction film, it may indeed be connected with the Kardashev scale, which measures the level of advancement of a civilization based on its ability to harness energy. If there were a Type 3 civilization capable of fully harnessing the power of an entire universe, it may have created an optimal simulation. Understanding reality in such a situation is a very convoluted matter. Researching the depths of cosmology and the origins of our universe leads us into a realm of profound mystery and ongoing scientific inquiry. The new images captured by the James Webb Space Telescope have reignited discussions about the very fabric of our world, testing established theories and provoking scientists to reconsider fundamental aspects of cosmological understanding. At the heart of this inquiry lies the theory of how things came to be, a foundation of current cosmology. According to this theory, around 13.8 billion years ago, the universe emerged from an extraordinarily dense and hot state, expanding rapidly and resulting in space-time and matter as we understand it today. This cosmic event is not simply an explosion within pre-existing space. Rather, it may encompass the very origin of space itself. The notion of a singularity, where gravitational forces are so intense that space-time becomes infinite, supports our understanding of this primordial epoch. However, the discovery of early galaxies by the James Webb Telescope challenges our assumptions about how quickly structures formed in the universe's infancy. These galaxies, identified within a few hundred million years of the Big Bang, appear remarkably evolved and massive, contrary to assumptions based on current cosmological models. One of the significant questions raised by these discoveries is the nature of cosmic expansion. According to the prevailing theory, expansion occurred within fractions of a second after the Big Bang, causing the universe to grow exponentially. This rapid expansion would explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, the new discoveries suggest complexities in the early universe's development that may necessitate adjustments to inflationary models. The formation of galaxies like those seen by the James Webb Telescope prompts cosmologists to reevaluate the conditions and processes governing the universe's early development. These galaxies, now significant in size and mass soon after the Big Bang, imply a density of matter that exceeds previous estimates. The mystery deepens when considering how such massive structures could form and evolve in a relatively short cosmic time frame. Furthermore, The discovery of these early galaxies raises intriguing questions about the nature of dark matter and dark energy, two elusive components that constitute the majority of the universe's mass and energy content. While dark matter is believed to provide the gravitational scaffolding essential for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the conventional Big Bang perspective. Some theories propose that our universe is merely one among many in a vast multiverse, each with its own unique physical laws and constants. These ideas, arising from advancements in string theory and quantum cosmology, suggest a more complex and interconnected universe than previously imagined. One idea gaining traction is eternal inflation, wherein universes continually emerge from a larger, expanding space. This hypothesis posits that our universe could be just one bubble among countless others, each with its own distinct properties. The challenge lies in finding observational evidence to support such theoretical notions as they push the boundaries of empirical verification. Another provocative hypothesis is that our universe exists within a simulated reality, akin to a computer-generated game. This idea draws parallels to advancements in artificial intelligence and computational science, where simulations can replicate complex systems with astonishing fidelity. If true, our perception of reality as a singular physical universe could be fundamentally altered, raising significant philosophical and scientific questions about the nature of existence. Moreover, advancements in observational cosmology continue to reveal the universe's vastness and intricacy. Telescopes like the James Webb Space Telescope, with its remarkable sensitivity and resolution, promise to unveil even more secrets of the universe. Future observations may shed light on the earliest moments of the universe, providing insights into its ultimate fate and the underlying rules that govern its evolution. Beyond observational cosmology, particle physicists are investigating the fundamental particles and forces that shape the universe. The mission to unify gravity with the other three fundamental forces, electromagnetism, strong nuclear force, and weak nuclear force, remains a central goal of theoretical physics. Concepts like quantum gravity and string theory offer potential frameworks for understanding these fundamental interactions at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the concept of time itself remains a topic of intense debate. The idea of time as a linear progression from past to future is challenged by quantum theories suggesting that time may be emergent or even elusive at the fundamental level. Understanding the nature of time within the context of cosmological models could reshape our perception of the universe's origins and evolution. Furthermore, the quest for extraterrestrial life continues to captivate public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars beyond our solar system, has expanded our understanding of planetary diversity and the potential for habitable conditions elsewhere in the universe. Future missions, such as the James Webb Space Telescope's investigation of exoplanet atmospheres, may provide evidence of biosignatures indicative of life beyond Earth. In addition to these scientific endeavors, social and philosophical reflections on the universe enrich our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration inspire thought and discussion across disciplines. As we stand on the brink of a new era in astronomy and cosmology, fueled by technological advancements and theoretical breakthroughs, we are reminded of the profound interconnectedness of everything, from the smallest subatomic particles to the vast cosmic structures spanning billions of light years. The universe reveals its secrets to those willing to explore and question. In conclusion, the exploration of the universe and the origins of existence is a journey that transcends disciplinary boundaries and challenges our most fundamental assumptions about reality. The discoveries made by instruments like the James Webb Space Telescope offer tantalizing glimpses into the early universe and provoke new inquiries regarding evolution and development. As we continue to unravel the mysteries of dark matter, dark energy, and cosmic expansion, we draw closer to a broader understanding of the universe and our place within it. Through collaboration among cosmologists, physicists, philosophers, and technologists, we embark on a grand journey to interpret the universe, a mission that promises to redefine our understanding of existence itself. Whether exploring the depths of black holes, charting the trajectories of distant galaxies, or investigating the nature of reality, every revelation brings us closer to unraveling the intricate tapestry of the universe. As we venture deeper into the cosmos, guided by curiosity and driven by a desire to grasp the universe's vastness and complexity, we are reminded of Carl Sagan's words, "Somewhere, something incredible is waiting to be known." This sentiment encapsulates the essence of scientific exploration, a continuous journey of discovery, wonder, and enlightenment that continues to inspire generations of scientists and thinkers alike. In the words of Albert Einstein, the most beautiful thing we can experience is the mysterious. It is the source of all true art and science. As we confront the mysteries of the universe, we are invited to embrace uncertainty, challenge our assumptions, and seek new perspectives that expand our understanding of the universe and ourselves. Thus, the exploration of the universe is not only a scientific endeavor but a profound human quest for knowledge and meaning, an odyssey that transcends the boundaries of space and time, inviting us to ponder our place in the grand tapestry of existence.